part 1 we did ionic bonding and properties of ionic bond, ionic structure, the properties of ionic structure, and so on and so forth. So we looked at that in part 1. Part 2 today we'll be looking at covalent bonding and probably maybe metallic bonding if need be. And we're going to wrap up this chapter for another chapter 4 for our next class. Now let's take a look at covalent bonding or the formation of covalent bond. First of all, what covalent bond happens between two or more non-metals. Okay, this is a bond, this is the pairing that happens with non-metals. You know, in the case of ionic bonding, we are talking about metals and non-metals. So a metal like sodium, we bond with by donating electrons with a non-metal like chlorine to form sodium chloride, which has a crystal lattice, which we've looked at in the previous class. Okay. Now, today's class, we're not going to be looking at metals and non-metals, we'll be looking at two metals, okay? So we say, if we take the analogy of non-metals to be like the ladies and the metals to be like the men, we say, in the case of this is the bonding between two non-metals, which means they don't donate, they don't give to each other, they always say, let's share, because that's what ladies do, they share their properties. They say, okay, let's say you bring this, like a cooperation, they cooperate. You have granite, I have gari, we can drink together. It's not like I give you my gari or you give me I give you granite. No, but in the case of man to woman, we can give the granite, we can give the gari, we can give everything that we have, as the case may be. So that's ionic bonding. In the case of ionic bonding, it's metal and non-metal. So keep this in your mind. And this involves the transfer of electrons in the case of ionic bonding, as we've seen in part 1. In part 2, it's not going to be that format. It's not going to be like that. It's not going to be donation. It's not going to be like transfer. It's going to be like sharing. We're going to share. You bring 2, I bring 2. You bring this number of electrons. I bring this number of electrons. So we're going to share together. We're going to like consume them together. I'm not going to give you mine. You're not going to give me yours. But we're going to collectively own yours and mine together. That's covalent bonding. So it's very convenient. So we call it covalent bonding. Okay? There's no ultimate sacrifice. You are not like shouldering the sacrifice. Like what they started in the West, 50-50. Okay? Like 50-50 sharing. Okay? So that's what it is. Like, it is what it is. So what we're saying here is that in the case of covalent bonding, the electrons are not donated. Like you're not going to give your outer electrons to another metal or to another atom or to another element. No, you're not going to do that. You're only going to share. He brings 2, you bring 2. He brings 1, you bring 1. Like that in that format, or in any characteristics, you go to bring together what you have and you go to share. So here it's about sharing. Okay, it's not sharing and pairing. It's not about I have it all, I give you all, I'm the master, I'm the boss, I can give. No one can give. We can both give. Okay? There's no fooling of each other, ultimate sacrifice, like is in the case of metal, the way metals sacrifice for non-metals. No, that's not what is happening here. So this ultimately between non-metals. So in that characterization, because it's between 2 non-metals or 3 non-metals, or between non-metals generally that participate in covalent bonding. So as a result of that, you're not going to see anyone that is going to donate. Or like ionic bonding, where you have full outer electrons, where you want to give your outer electrons that is not in full contest, so any of the non-metals that needs it. But this is not the case in the case of covalent bonding. Okay. Now, covalent bonded substance may consist of small molecules and or giant molecules. Sometimes just small molecules and giant molecules. Now, when 2 or more atoms are covalently bonded together, we describe them as molecules. So when 2 atoms bond together, let's say for example chlorine, 1 chlorine atom bond with another chlorine atom. Okay, 1 chlorine atom bond with another chlorine atom. This will become what? Chlorine molecule. This will become chlorine molecule. It will be 2 atoms of chlorine, which we call chlorine molecule. It will become 2 atoms of chlorine like this, which we call chlorine molecule. This is 1 molecule of chlorine, but with 2 atoms. 1 molecule of chlorine. So when atoms of non-metals bond together, we simply call them molecules. We simply call them what? Molecule. When hydrogen, 2 atoms of hydrogen bond with 1 atom of oxygen to form water, then we call this what? One molecule of water, with 2 atoms of hydrogen and 1 atom of oxygen. Okay, so that's what we call them molecules. So when atoms bond together covalently, we call them molecules. Molecules. And we can represent this with a cross and dot like we did in ionic bonding in part 1 of chapter 3. So it's same logic, but in this case, the only difference is that no single atom is donating or is giving or is transferring totally to the other atom. What they do is that they contribute and then they evolve. They contribute, they overlap, and then they form a giant micromolecule, or they form a covalently bonded molecule. Now let's take a look at what we have. The diagram to show the formations of a covalent bond. Now let's take a look at a covalent bond. And in this first case, we're looking at chlorine. Okay, now you see each needs 1 electron. You remember this chlorine. This is a chlorine, this is a chlorine, even if we use a crosser dot. Crosser dot is just to show that there are 2 atoms, like 2 separate atoms, even if they are the same atoms of the same element, okay? This is a chlorine atom, this is a chlorine atom, okay? But we use cross here, and we use dot here to signify that, okay, they are 2 separate things, like, okay? Even if they are 2 spoons, they're 2 spoons that are similar, but they are 2, okay? So even if they are twin, they are similar, they are 2. So that's why we use cross and dot to differentiate them. Now let's take a look at it. If you look at the outer shell electron, we're only focusing on the outer shell electrons. If you look at the outer shell electron of a chlorine atom, it has several electrons in the outer shell. This white one shows that is in need of, meaning it does not exist. It's in need of 1 electron to complete its outer shell. Similarly, this one has 7 in the outer shell. This white one is showing that it needs 1 electron to complete its outer shell. So you need one. Why should I give you this one? So I will have 6. So what help does it do for me? If I give you 1, you become 8, I become 6. I lose more energy. I lost my status. I do not complete my outer shell electrons configuration. I do not obey the octet rule. Neither do I obey any rule. So what good will it be to me if I give you this 1? So I made you better than myself. That's what it is. I made you better than myself. Why should I make you better than myself? We should share. Now, this is what it is. Now, in covalent bonding, this is what they will do. Okay, you say, oh, you have 1 here, I have 1 here. Why don't we overlap here? You know, I'm supposed to have 2 here. You are supposed to have 2 here, right? To complete 8 here and to complete 8 here. So when we overlap, it's a logic. When we overlap, you bring this your 1, this your 1, that's the 7th one. I bring this my 1, that's the 7th one. We overlap here. When we overlap, if they count this my circle, I will be 8. If they count this your circle, you will be 8. So when they're counting yours, you are the one that owns this 8. We include this mine, 1 red one. So when it's my turn, it will be mine. So it's like we're both using these 2. When the time arises, I want to use, okay, I use. When the time arises, you want to use. So we both have 8 in our outmost shell electron. So this is 1 chlorine atom. This 1 chlorine atom bond with another chlorine atom to form what? A chlorine molecule. To form what? A chlorine molecule. To form, permit me to say plus for bonding in this regard. Okay, so to form a chlorine molecule. To form 1 molecule of chlorine. To form 1 molecule of chlorine. So in this way, everyone is happy. You got your 8 in your outmost shell. I got my 8 in my outmost shell. So we're good. We're good. It becomes a molecule of chlorine molecule. Okay? So we're good. Life is good. You got what you want. I got what I want. You know, we only consider only the outer shell electrons. The other ones are intact. Even if we don't draw them here, we don't show them here, they're there. Okay? Okay, so this is what we call covalent bonding between non-metals. This is what we call covalent bonding. It's about an understanding, sharing, you know, like bringing together our resources to form a giant, okay? Where none of us will be suffering. Okay, that's what we call covalent bonding. And if you take a look at this, it's chlorine to chlorine single bond. Why is it chlorine to chlorine single bond? Because we're going to do oxygen to oxygen double bond. We're going to look at that. This is chlorine to chlorine single bond. You see, I draw 1 bond here. If I'm doing for oxygen, it's going to be like this. The bonding will be like this. Oxygen to oxygen double bond. Why? Why? In bonding, in covalent bonding, you need to know this. In nitrogen, is nitrogen to nitrogen triple bond. Why? You need to know this. If you don't know this, you're lost. You're lost, okay? You're lost in this chapter. Okay? So nitrogen is nitrogen to nitrogen triple bond. What it simplify, or what it implies is the, chlorine is the only loop, they're only sharing one. You bring one. So since we're bringing one, the bond is just a singular bond. Okay? It's just a singular bond. In the case of oxygen, oxygen is 2,8, right? 2,8. So one atom of oxygen has electronic configuration of 2,8. The first shell has 2 electrons. The second shell has 6 electrons, right? For this one atom of oxygen. Okay, let's say for this one atom of oxygen. For the second atom of oxygen, the story changes a little bit. The dynamic changes a little bit. For this second atom of oxygen, same thing, right? It has 2,8. Now, what this implies is that they're both looking for 2 to complete their utmost share electrons. This one is looking for 2, this one is looking for 2, so we're going to bring 2. I bring 2, you bring 2. That's why it's a double bond. Oxygen to oxygen double bond. In the case of this one, it's 2,5 because the atomic number or number of protons is 7. So this atomic number is 7. The electronic configuration is first share we hold 2 electrons, second share we hold 5 electrons. So it's looking for 3. This one is looking for 3. This one is looking for 3. So this one is going to donate 3. This one will donate 3. Okay? So if I'm doing the outer electron of nitrogen, let's say this is a bonding in nitrogen atoms to form nitrogen molecule. Here, let's assume we have this cross for this side. Okay, I'm doing for this one, it has 5, right? So I can put the 2 here, the first 2 here. Let's say I use cross for this one. Let's say I use cross here. Right? Because it has 5, it's going to give 3 here. That's why it's triple bond. It's going to give 3 in this donation overlap, this circle. It's going to give 3. So I'm not drawing these 2. This 2 is not this 2. Mind you, this 2 I took from here. This 2 is from the first share. We are not drawing the first share. I'm only showing we're only showing the outer share. If you want to draw the first share, then these 2 will be inside here. Okay, but we're not showing then the nucleus is inside here, the nucleus, where you have the protons and the neutrons. They're inside the nucleus. Those ones are inside here. Okay, but that's not what we only represent the outer shell, which means I'm only using this 5. For this 5, I will take 2 here, but I will donate 3 in the center. So I have 3 cross here. 1, I give space, I draw second 1, meaning this atom of nitrogen, this nitrogen atom will donate 3. This nitrogen atom will donate 3. And then I'll have the third one. Okay. Now, let's go to the other nitrogen atom. The other nitrogen atom will also donate 3. This one. This other nitrogen atom will donate another 3. Okay, that's why it's triple bond. This one will donate 3. Okay. It has 5 in the outer shell. So this one we're using dot. Out of the 5 in the outer shell, 2 will be here. And then you donate 3 in the overlap, in the sharing space. So I donate 1 here, 1. I donate another 1, 2. For this one, for this other atom. I donate the third one here, 3. Donate the third one here, 3. So you can see, now the logic is, here you have 6 all together. Because this one donate 3, this one donate 3. So you have 6. So if you count 6, 7, 8. So you can see the outer shell of this one is complete 8. Because the objective is to have 8 in this loop, in this circle. Is to have 8. Similarly, is to have 8 also in this other circle. If you're considering for this atom, if you're considering for this nitrogen atom. So if you consider for this nitrogen atom, you have 1, 2, 3, 4, 5, 6, 7, 8. So it's also complete 8. So that's why it's a triple bond. So you'll be wondering, why is it triple bond? Because each atom donates 3. This one donates 3, this one donates 3. That's why it's a triple bond. This one donates 3, this one donates 3. In the loop, in the overlap. We're not saying they have 3 in the outer shell. They have 5. You donate 3, the remaining 2 you put you put S-square outside. You put S-square here, right? This will also donate 3 in this overlap, and then or intercept, you can call it intercept. In this intercept, you donate 3, and then the other 2 you put outside here. So if you count, it's still 5 for this one. If you count the yellow, 1, 2, 3, 4, 5. The yellow is 5, which is this 5. In the auto share. Similarly, for this one is 5, the blue. Okay, so that's what's happening. Now let's go take a look. If it's oxygen, this one will donate 2, this one will donate 2. Meaning in the overlap for oxygen there will be 4. 2 from this oxygen, 2 from this oxygen. So which means 4 here. Right? If you donate 2, it's remaining 4. So 4 will be in this overlap. The remaining 4 from here will be spread out way this way. So 4 out, 4 in the overlap, will complete 8 for oxygen. If you do the oxygen, double bond. Okay, now let's take a look at that. I hope you get what we're saying. We start with the single one. We start with hydrogen. Hydrogen has 1 atom or one electrons, right? 1 proton, 1 electron. So hydrogen just has 1. Just has 1. So since it has only 1, since it has only 1, let's say this one is for cross. That cross, since it's only 1, no need to put it outside. Just bring it here. Put the cross here. This one has only 1. Let's say it's dot. Put the dot here. So that's what's happening here. This one has 1 electron. No need to put it outside just because. Because you know why? Because first share must be 2. So it means this atom's first share is 2 now. And this atom's first share is 2. First share must be 2 for every atom. First share must be 2 electrons for every atom. Second share, maximum 8. Third share, maximum 8. Every other share, maximum is 8. Is that okay? So that's for this bond. It's called single bond, single covalent bond. To form a hydrogen molecule. One hydrogen atom bonds covalently, undergo a single covalent bond to form hydrogen molecule. To become what? To become this hydrogen molecule, like this. H2, to form H2. One atom plus another atom to become H2. Now this is 1 molecule of hydrogen with 2 atoms. Atom is the small subscript down here. The molecule is the number we write here. If I write 2 here, it will be 2 molecules of hydrogen. But as it stands, without a number means 1. Without a number means 1. So it's 1 molecule of. This is basic science that you should be very familiar with. Okay, in the second single covalent bonding, it's that of chlorine, which we've explained already. And second single covalent bonding is that of chlorine, which we've showed already, or which we've demonstrated already. Now let's take a look at that. We say chlorine has 7, right? So you have 7. This chlorine atom has 7, and this chlorine atom also has 7. So what they will do, because it's single in the overlap, when you draw the overlap, this one will bring 1. And this one will bring 1, which is this red. So they will now have 2 here in the overlap. So if you count this way, to be 8 electrons in the atmosphere of this chlorine atom, and it will also be 8 electrons in the atmosphere of this chlorine atom. So this is what we call covalent bond. Covalent bond is that you bring from your electron in your atmosphere, you bring some, I bring some, we form what? We form a molecule. We're good together. Is that okay? So now let's go to in the case of water. Now when we have just more than 2 bonded together. In the case of water, oxygen is here. This oxygen will bond on the right with 1 hydrogen atom, and we bond on the left with another hydrogen atom. Remember, we say hydrogen is H2, right? There are 2 atoms of hydrogen. When you write your water, you say H2O, meaning I write oxygen like this, single bond to hydrogen on the left, on the right, and single bond to another hydrogen atom on the left. Right? Something like this. This is what happens. This is the bonding that takes place. This is the bonding. What it means, you know, oxygen has 6 electrons in the atmosphere and it's looking for 2. So since it's looking for 2, it will donate 1 on this side. The oxygen is the red one. So out of the 6, it keep 2 here, it keep 2 here. Right? That's 4. The remaining 2, you will share one with hydrogen on the left, and you will share one with hydrogen on the right. Right? So make it 6, make it O6 for the oxygen. The hydrogen has only one. That one, he will only share it here with this overlap with oxygen. He will only share his other electron again with this one on the other side. So that's why it's like this. That's why it's like this. The bond is like this. Is that okay? So this is the covalent bond. This bond is called covalent bond. Single covalent bond. This is called single. Why is it single? Because it only gives one at every overlap. At every side, it bonds with hydrogen. It only gives one atom, and hydrogen gives one atom. On this side, it also gives one atom, hydrogen gives one atom. I hope this is clear enough. Okay? Now let's move on to a more complex one, methane. Methane is CH4. What it means is that one carbon will be surrounded with 4 hydrogen. One carbon atom is surrounded with 4 hydrogen atoms. So if you want to draw the logic, you draw C. So you draw 1 hydrogen to the top, 1 hydrogen atom to the top. Okay? Another hydrogen atom to the right. Another hydrogen atom to the right. Another hydrogen atom to the left and to the bottom side, downside. So this is what methane is. So meaning carbon, you know carbon, what's the atomic number of carbon? 6. So atomic number is 6. So first share we take 2. Second share we take 4. So this atomic number is 6. Remember carbon, atomic number. You must know the first 20 elements in the periodic table of heart. You must know the first 20 elements of heart. Because if you don't know the first 20 elements, every time you go to periodic table. But you need the periodic table. Even if you don't know, you can consult your periodic table. It's allowed. It's not a crime. So what it means, this carbon, since it's bonding on all 4 sides, it will give 1 to the top with hydrogen, 1 to the left with hydrogen, 1 to the right with hydrogen, 1 to the bottom side with hydrogen. All the 4, it will share them. All the 4 atoms in the outermost shell, it will give them out, right? And then hydrogen will bond with one here, 1 atom it has 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 here. Okay? So after the ammonia thingy, we look at the tutorial. Is that okay? We're supposed to start with the tutorial, but after this one we do. It doesn't matter which one we start with. We can start with ourselves and we end with tutorial. It doesn't matter. Okay, so for this carbon, it's easy because it has 4 electrons in the atmosphere. The carbon is the red one. The carbon is the red one. So it gives this one here with hydrogen. It shares with hydrogen here. These hydrogen atoms bring this cross, brings this atom. The carbon brings this one. Okay. So here, this carbon is the center. Look at the carbon here. It's at the center. Okay. It's like you draw. This is the carbon. Okay. At the center, this is the carbon. On every side, it bonds with hydrogen. Here, it bonds with hydrogen. Here, it bonds with hydrogen. Can make the hydrogen a bit smaller so that it's more understandable. Here, it bonds with hydrogen, and here it bonds with hydrogen. Okay. So the carbon, already let's assume is the dot one. The carbon is the dot one. So we have dot here. The carbon is the dot one. We have a dot here from this carbon because there are 4 electrons in the atmosphere. We only use the electrons in the atmosphere. Don't say, oh, carbon has 6, and then you share 6. No. We only use the electron in the atmosphere to do the bonding. So you must draw the electrical configuration like this first, so that you know the number of electrons in the atmosphere that undergoes the bonding process. Is that okay? So it has 1 here, and then it has 1 here. It bonds with 1 here. Now, what fills the hydrogen now? Let's take a look at all the hydrogen. All the hydrogen. This hydrogen, this hydrogen, this hydrogen. Now, let's take a look at what hydrogen has to contribute, what hydrogen brings to the table, what hydrogen brings to the union, what hydrogen brings to the togetherness. Hydrogen brings its only 1 electron it has. Hydrogen brings its only electron that it has to contribute and say, oh, you know what? I also can contribute something. I am not empty. I can contribute. So hydrogen brings its cross here. This hydrogen atom brings its only 1 electron. This hydrogen atom brings its only 1 electron. This hydrogen atom brings its only 1 electron. This hydrogen atom brings, this hydrogen atom brings is only 1 electron. So if you look for hydrogen, you know hydrogen is complete 2 for the first shell. It's okay? Yeah. And then this one complete 2 for its first shell. Hydrogen first shell must be 2. Every atom, its first shell must be 2. So this hydrogen first shell is 2. This one, hydrogen first shell is 2. Now the carbon is 8. Count all of them. 1, 2, the outer shell of carbon is 8. 1, 2, 3, 4, 5, 6, 7, 8. So for carbon, it's complete 8. And for hydrogen, they are all complete 2, 2, which is required for hydrogen atoms. Okay, so that's what is shown here. That's what is demonstrated. For the case of chlorine, remember ammonia is NH3. So meaning 1 nitrogen atom is bonded with 3 hydrogen atoms. Okay, with 3 hydrogen atoms. You can draw this whichever way you want. You draw 1 nitrogen. You know nitrogen has 2,5, right? 2,5 nitrogen. So meaning it has 5 to bond with. Out of those 5, it's going to give 1 here, 1 here, 1 here. So the nitrogen is this red one, this nitrogen. So first, this first 2 from here, this 5, it will keep 2 anywhere it likes. And then, the remaining 3, it will give 1, it will share 1 with hydrogen this way, 1 with hydrogen this way, 1 with hydrogen this way, and 1 with hydrogen this way. That's ammonia, NH3. The H must be 3 sides, from 3 sides. So these are this is the first nitrogen contribution here, nitrogen contribution here, nitrogen contribution here with this hydrogen. Nitrogen contribution here with this hydrogen. Nitrogen contribution here with this hydrogen. Now this is the hydrogen contribution, the cross. Okay? This is the hydrogen contribution here, the cross. This is the hydrogen contribution here, this cross. Now you can see hydrogen is complete 2 in its first share. This hydrogen is complete 2 in its first share. This hydrogen is complete 2 in its first share. And then the nitrogen is complete 8. You can count 1, 2, 3, 4, 5, 6, 7, 8. So nitrogen is complete 8. So this is a covalent bonding. Okay? Before we go further, the same with hydrogen chloride. Hydrogen chloride, right? 1 atom of hydrogen bond with there's chlorine. Chlorine has 1. It has 7 atomos shell. That 7th one bond with hydrogen for chlorine to be 8 here and for hydrogen to be 2. Once hydrogen is 2, hydrogen is okay. Okay, now let's take a look at the tutorial before we go to covalent bond in complex molecule. Let's take a look at our tutorial before we go to covalent bond in complex molecule, right? Okay, so you're welcome. Please pay attention to our covalent bond.
In this video, we will be looking at how covalent bonds are formed. A covalent bond is formed when 2 non-metal atoms share a pair of electrons. Each atom gains a full outer shell of electrons, equivalent to a noble gas electronic structure. A hydrogen molecule is formed by covalent bonding. The shells of each atom overlap and share electrons. Now each atom has a full shell. The bond is held together by electrostatic attraction between the nuclei and the shared pair of electrons, forming a molecule. So we know that molecules are formed by covalent bonding. A hydrogen molecule is a good example. Remember that hydrogen only has 1 electron in its outer shell, as it is in group 1. To gain a full shell, it requires 1 more electron, which can come from another hydrogen atom. The same mechanism occurs. The shells overlap, and a pair of electrons is shared between the 2 atoms, forming the covalent bond. This type of diagram is called a dot and cross diagram. This means we can identify which atoms the electrons have come from. The covalent bond is represented by a line between the 2 atoms. The size of the hydrogen molecule is typically 0.074 nanometers. Chlorine has 7 electrons in its outermost shell, as shown by the red dots and blue crosses. Chlorine atoms need 1 electron to achieve a full outer shell. The gaps here are shown by the white dot and cross. To form a chlorine molecule, the outer shells of chlorine will overlap, forming the single covalent bond. and now each chlorine atom has 8 electrons. This again can be represented by a straight line between the atoms. Other halogen molecules will also bond in the same way. As you do not need to show the inner electron shells, a molecule of bromine or iodine will appear the same. Even if you are drawing a dot and cross diagram using 2 of the same type of atom, you should use dots for one atom and crosses for the other. Water has the formula H2O. There are 6 electrons in the outermost shell of the oxygen atom, so it requires 2 more. As we know, hydrogen only requires 1 more. The oxygen atom can share 1 electron with each hydrogen atom by overlapping its outer shell with 2 hydrogen atoms and forming 2 covalent bonds. On the oxygen atom, there are 2 lone pairs of electrons. Make sure you include these, as otherwise the oxygen atom will only have 4 electrons. We can represent the water molecule using this displayed formula. In an exam, there will be a mark for making sure all atoms in the molecule have the correct number of electrons. So make sure you double check your molecule before moving on. Let's now have a look at a worked example. Covalent dot and cross questions are usually worth 2 marks. You are most likely to be given the template or displayed formula of the molecule in the exam, which you can use to draw the dot and cross diagram. If not, you will be given a clue as to the structure, so read the question stem carefully. Also, check the question to see if any specific symbols have been given for electrons of each atom. For ammonia, nitrogen is the central atom, and there are 5 electrons in the outermost shell. Therefore, we know that the nitrogen atom requires 3 more electrons. The first step is to draw in the nitrogen electrons using a dot. Then add in the electrons for the bonds using crosses for the hydrogen electrons. This is worth 1 mark. Before you move on to the next question, always check the atom has the correct number of electrons, as there is a second mark for this. In this case, nitrogen has 1 lone pair of electrons. In this example, you are asked to complete the dot and cross diagram for methane. Use the template given to you and look out for specific symbols, so crosses for hydrogen electrons and dots for carbon electrons. Again, follow the steps. Draw in the outer electrons of the central atom, in this case carbon, which is a group 4 element with 4 electrons in the outermost shell. The question has asked you to give dots as the symbol for the carbon electron. Draw in the hydrogen electrons using crosses. Carbon now has a share of 8 electrons in its outermost shell, and hydrogen now has a share of 2 electrons. The result is 4 single covalent bonds. Double check that each atom has the correct number of electrons. The bonds are worth 1 mark, and the correct structure is worth another mark. In summary, you should know that a covalent bond is formed between 2 non-metal atoms. A single covalent bond is 1 shared pair of electrons, which can be drawn using dot and cross diagrams. A dot and cross diagram represents the number of electrons in the outer shells of each atom in a molecule. Don't forget.
Okay, so we've seen that basic one. Let's see the next one, the tutorial for the next one. Let's see the tutorial for the next one before we go to molecular compounds. Covalent bond in complex molecules. Let's see the tutorial, and then before we move on.
In this video, we will be looking at covalent bonding in complex molecules. If a single covalent bond contains 1 pair of electrons, then a double bond must contain 2. An oxygen molecule contains a double bond. Oxygen has 6 electrons in its outermost shell, so it requires 2 more. When an oxygen molecule is formed, the 2 atoms overlap and share 2 pairs of electrons. This is the double bond. This now means that each oxygen atom has a share of 8 electrons. A double covalent bond is represented by 2 lines between the atoms. Ethene has the formula C2H4. It is an alkene and therefore an unsaturated hydrocarbon, and you could be asked to draw the dot and cross diagram for this molecule. Each carbon atom requires 4 more electrons, and each hydrogen atom requires 1 more electron. When the shells come together and overlap, one double bond containing 2 pairs of shared electrons is formed between the 2 carbon atoms, and 4 single bonds are formed between the hydrogen and carbon atoms. Double check that each carbon atom has a share of 8 electrons, and each hydrogen atom has a share of 2 electrons. The displayed formula will contain a carbon-carbon double bond and 4 carbon-hydrogen single bonds. You could also be asked about a nitrogen molecule which contains a triple bond. Nitrogen is a diatomic molecule, which means it consists of 2 atoms covalently bonded together. Each nitrogen has 5 electrons in its outer shell, so requires 3 more electrons. When the shells come together and overlap, one triple bond containing 3 pairs of shared electrons is formed. The triple bond is represented by 3 lines between the atoms. This bond is very strong and would require a lot of energy to break, meaning nitrogen is a very unreactive gas. Double check that each nitrogen atom has a share of 8 electrons. Dot and cross diagrams are usually worth 2 marks. The first worked example asked you to draw the dot and cross diagram of methanol. Pay close attention to the question, as you may be asked to use specific symbols for electrons for particular atoms. Use the given template or displayed formula to help you. As we can see, methanol only contains single bonds. Therefore, only 1 pair of shared electrons needs to be drawn where the atoms overlap. Draw in the outer electrons of the carbon and oxygen atoms. Make sure that you use the correct symbols for the carbon and oxygen electrons. Form the remaining single bonds using the correct symbol for the hydrogen electrons. This scores the first mark. Check each atom to ensure there are the correct number of electrons. Carbon and oxygen should each have a share of 8 electrons, and the hydrogen atoms should have a share of 2 electrons. The lone pairs score the second mark. Here, you are asked to draw the dot and cross diagram for carbon dioxide. Again, check if any specific electron symbols are given in the question, and use the given template or displayed formula to help you. Here, we can see carbon dioxide contains 2 double bonds. Write in the outer electrons of the carbon and oxygen atoms, making sure that you include double bonds, so 2 pairs of shared electrons. This scores the first mark. Check each atom to ensure that there are the correct number of electrons. Each carbon and oxygen atom should have a share of 8 electrons. The lone pairs score the second mark. In summary, you should know that a single covalent bond contains 1 pair of shared electrons. A double covalent bond contains 2 pairs of shared electrons, and a triple covalent bond contains 3 pairs of shared electrons. You should also be able to draw the dot and cross diagrams for nitrogen, ethene, methanol, and carbon dioxide.
Okay, so we've seen for double bond and triple bond, right? We've seen for double bond and triple bond, and the last one is properties of simple molecular compounds. Last one is the property of simple molecular compounds. Let's listen to the tutorial on that, and then we wrap up from here.
This video looks at the properties of simple molecular compounds. Simple molecular compounds are made up of molecules that contain just a few atoms covalently bonded together. They have low melting and boiling points, so these compounds are usually liquids or gases at room temperature. There are only weak forces of attraction between the molecules, unlike metallic, ionic, or giant covalent structures. As the molecules increase in size, the melting points and boiling points generally increase. Simple molecules have poor electrical conductivity. Extended students need to be able to explain why simple molecular compounds have low melting and boiling points and do not conduct electricity. Molecules are bonded together by strong covalent bonds, but there are weak intermolecular forces of attraction between the molecules. These intermolecular forces are not very strong and are easily overcome. This is why at room temperature, simple molecular compounds are usually gases or liquids. Some will be solids, like sulfur, but these will still have a low melting point. When a simple molecular compound melts or boils, it is only the intermolecular forces that are overcome. The bonds do not break. Melting and boiling points also depend upon the size of the molecules. As a molecule increases in size, the melting and boiling point increases. Take ethane and butane as an example. The alkane ethane has a relative molecular mass of 30 and a boiling point of minus 89 degrees Celsius. A slightly bigger alkane butane has a relative molecular mass of 58 and a higher boiling point of minus 1. For a substance to conduct electricity, there must be free electrons or ions that are able to move and carry a charge. Simple molecular compounds do not have these, so cannot conduct electricity. They act as insulators. Examples include coating on electrical wiring or electrical sockets. Let's have a look at an exam-style question. In this question, you are being asked to fill in the table to show the electrical conductivity for solid diamond and solid sulfur. They are both covalent compounds. The only difference is that diamond is a giant covalent structure and sulfur is a simple molecular structure. These compounds do not generally conduct electricity when solid or molten, so you will need to write does not conduct electricity to gain each mark. For part 2, you are asked to give one piece of evidence from the table that shows that sulfur is a simple molecular substance. Sulfur is the only substance that has a low boiling point. You know that simple molecular compounds have low melting and boiling points, so this is the piece of evidence that will gain you the mark. This next question is for extended students only. You are given 2 different compounds, magnesium fluoride and carbonyl fluoride. You should know that magnesium fluoride is ionic, as it contains a metal and non-metal. Remember that ionic compounds have a high melting point. Carbonyl fluoride is a simple molecular compound with strong covalent bonds between the atoms within a molecule, but weak forces of attraction between the molecules. During melting, it is the weak intermolecular forces that are overcome, not the strong covalent bonds. Therefore, carbonyl fluoride has a low melting point. Many students make the mistake of saying that the bonds are weak and easily broken. You must specify that it is the forces between the molecules that are weak. In summary, you need to know that simple molecular compounds are bonded by covalent bonds and tend to be gases or liquids at room temperature. Their properties are low melting and boiling points, and they do not conduct electricity. Extended students should be able to explain the properties of simple molecular compounds. They have low melting and boiling points due to the fact that the weak intermolecular forces are easily overcome. They do not conduct electricity as there are no freely moving charged particles in the structure. Don't forget to check out.
Okay, so this is the third part of the. Okay, so now let's quickly take a look to round it up. To round it up, we've talked about everyone we've talked about, and the tutorial has also talked about. We just show for triple bonding. We've already explained this. We say nitrogen has 5 electrons in the atmosphere, so it gives 3 here for the overlap. This other atom gives 3 for this overlap. So these are the 2 low pair electrons. So when you remember to put these 2 low pair electrons, these 2 low pair electrons, you get 1 mark. And when you write the 3, 3, which is 6 electron in the overlap, you get another 1 mark when you do this in the exam. Okay. In the case of ethene, let's take a look at ethene. In the case of ethene, you can see carbon is bonded covalently with another carbon. So this is a double bond. It means each carbon atom will bring 2. Carbon has 4, right? Carbon itself has 4 electrons in the atmosphere. So this 4 for this carbon could include this pink, this pink, this pink, this pink, blue, sorry, this blue, this blue, this blue, this blue, right? So this is for this carbon. This for this carbon. For the other carbon is this cross, deep blue or navy blue, cross. This cross, this cross, this cross. See, it's 4, 4. So what carbon will do, because it's double bond, this carbon will bring 2. That's why you see this light blue. And this other carbon brings this 2, this cross. So it's 4 here. Now on this side, this carbon will bring this 1 electron, and this hydrogen will bring this red electron. So the hydrogen is complete in the atmosphere here. Then the hydrogen here also bring this 1 electron in this atmosphere, and this carbon on this side brings this blue on this side. So similarly here, this carbon brings this 1. You know, it remains after donating 2, it still has 2. The one it gives here and the one it gives here. And then this hydrogen brings this 1. So you can see hydrogen is complete in the atmosphere, in its shell. This carbon, if you look, it will be 8 for this carbon atom. Similarly for this carbon atom is also 8 electrons after bonding with double covalent bonding here, okay, which is the overlap bonding, and then also bonding with hydrogen here and bonding with hydrogen here. So at the end of the day, this is ethane. This is ethane. Ethene, not ethane. Ethene, okay, which is organic chemistry you're going to study later. But this is the bonding. Now let's take a look at the case of methanol. A methanol is CH3OH. CH3OH. Okay, let's quickly take a look at this because we've had them also in the tutorial. CH3OH. So what this means is that the first carbon will be bonded 3 sides with hydrogen. So carbon has 4 in its atmosphere, so it's going to share with 3 hydrogen atoms. So this carbon is going to give 1. Hydrogen brings 1 here. This hydrogen brings this cross. This other hydrogen brings this cross. So the carbon brings this blue, light blue. This carbon brings this other light blue. So carbon still has 1. So the one it has, it will bond with what? With oxygen. This carbon will also bond with, after bonding 3 sides, if you draw this, after bonding the 3 sides, 1 here, 1 here, 1 here. Carbon will bring 1, 1. Hydrogen will also bring 1, 1. That's what you see here. That's what you see here. That's what you see here. Carbon brings 1. The carbon brings this light blue. The hydrogen brings the cross. Okay? So that's what you see in this side. Now on this side, it's going to bond with oxygen. In bonding with oxygen, it will bring the last one. You know it's 4. It has 4 electrons in the atmosphere. You bring the last one. It has given 1 to hydrogen here, bonded 1 here with hydrogen, bonded here with hydrogen. The remaining one, it will bring here for oxygen, to bond with oxygen. The oxygen will bring 1 also. So oxygen here is now 2. Remember, but oxygen, you know, it has 2 pair here, 2 lone pair here, and 2 no pair here. And then oxygen, because it's 6 in the atmosphere, it still has 1 left. That 1 left is going to bond with another hydrogen atom. It's going to bond with what? Another hydrogen atom. Remember, hydrogen is cross. So that cross comes here with this oxygen, which is red, this oxygen, which is red, and then we have this structure. This is the covalent bond that occur in it. It's a mixture. This one is a mixture. It's all a single covalent bonding happening at every interval. Now let's take a look at carbon dioxide. In the case of carbon dioxide, we have the carbon. Carbon has 4 electrons in the outermost shell, right? It has 4 electrons in the outermost shell. So it's going to share 2 with 2 of that of oxygen on the left, and 2 with 2 of that of oxygen in the left. So the carbon has no pair electron remaining. Because it has 4, it will share 2 with oxygen. It will bring 2, oxygen will bring 2 on this left side, and it also bring 2, the overlap on the right. It will bring 2, and oxygen will bring 2. So that's what's happening here. This carbon brings these 2, this cross. Sorry, this carbon brings this 2 red one. This carbon brings these 2 red one. Then the oxygen brings these 2 cross. Okay, so becoming a double covalent bond here. A double covalent bond here in the overlap. And on the other side, same thing happens. On the other side, same thing. Brings 2 here. So it does not have a low pair one outside. And if you count, it's still going to be 8 because it bond 2 and with 2 of oxygen, meaning 4 here in the low pair here in the overlap. Also, similarly, in this overlap also has 4. So which makes it 8 here. But if you look at this one, it has 4 low pair. 2 here, 2 here. 2 low pair here, 2 low pair here. And everything 8 for this oxygen, and so on and so forth. Everything also 8 for this oxygen. This is the covalent bonding, double covalent bond that occur in carbon dioxide. Now, in the case of properties of simple molecular compound, which we've talked about in our tutorial, we say that they have very strong bond. They have strong bond within the molecule. Within the molecule, they have strong covalent bond. Within the molecule, they have strong covalent bond. I think we changed the color. So for simple molecular compound, within the molecule, they have strong bond, but they have weak intermolecular forces when you link them up with another similar one. When you link them up, they have weak intermolecular forces. So this is why they have low melting point, the weak intermolecular forces. So if they ask you why are in the exam, why are simple or giant molecular force molecular compounds, covalent compounds, why do they have low melting point? Is because of the weak intermolecular forces. Not the bond. The bond is not weak. The bond between each link is a strong bond. It's a strong a strong covalent bond. Between each link, the bond within each link is a strong covalent bond. The bond. But the bonds are linked together by weak intermolecular forces. These bonds are linked together because you need many of these to make that giant macromolecule. If you want to make a giant macromolecular compound, you need many of this type to be linked together. The force that link them together is what is weak. The force linking them together is what is weak. So if they say, why do they have low boiling point and low melting point? You say they have weak intermolecular forces. They have weak intermolecular forces even though they have strong giant covalent bond. Even though they have strong covalent bond. Okay? Now, why do they not conduct electricity? Because they don't have free electrons or ions to move about. They don't have delocalized electrons to move about. That's why they cannot conduct electricity. Is that okay? They use as insulator. So with this, we've come to the end of our today's class. Thank you for joining us.